Hello everyone. Welcome to Summer School 2025 by C5 IIT Madras. This is Horizon, the Physics and Astronomy Club of IIT Madras, and myself, Aditya Goyal, the coordinator of the club. So today I'll be taking this session along with my co-coordinators, and this session, as the title suggests, will make you ponder upon the question that what if the apple never fell on Newton's head? If it actually ever fell on Newton's head. So we'll think about how would the state of mechanics be without Newtonian mechanics, and as the description might have already suggested, we'll explore how Lagrangian mechanics and Hamiltonian mechanics is helping us to make mechanics easy. So before obviously going on into the details, I'll start with the very basics, and I'll like to brief you through with some notation used here. So first of all, vectors will be expressed as column matrices where each entry is a certain component of the vector. So for those of you not familiar with the concept of matrices or column matrices, the one at the bottom right is what is a column matrix, and each entry of it represents a certain component of the vector. So suppose I have a position vector. So 5 will be, for example, the x component, 8 will be the y component, and 2 will be the z component. And nextly, matrices will be represented using bold symbols. The subscripts of matrices represent the row and column number of a specific matrix component. So suppose you see matrix with the name M with a subscript I comma j written on it. So we are referring to the component of the ith row and the jth column of a matrix. And a general subscript of subscript represents some form of index. We'll see when you'll see in the examples. And for example, if there are n possible values of x, we can represent them compactly as xi, x subscript I, where I is an index which ranges from 1 to n. So suppose I have a quantity which can take n different values. So instead of writing them separately, I'll rather write it as xi, where I represents the ith component of out of all the n possible values. Now, if common index variables are present on the same side as an equal to symbol or in an expression, then we usually assume that you must sum over all possible values of that index. So, for example, we have this integral over here, which says del of integral pi qi dot minus k dt equals 0. So again, for the notation, this qi dot means derivative of qi. We'll in the next slides we'll see what is the derivative. I'll explore that also. And this means that first the index I means that we have to sum over all possible values of the index I, again whatever the possible values of p and q can be. So we'll vary I accordingly, and we'll consider all possibilities and do the summation in that manner. Next, the partial derivative of a function f with respect to its independent variable xi is written in the following form. So this inverted 6 that you see is called del, and this is a way of writing the partial derivative of f with respect to its subscript, that is xi in this case. Now, since I mentioned derivatives and partial derivatives, what actually are they? So, in simple words, derivative is nothing but a tool to help us understand how does a quantity vary in accordance with some other quantity on which it's dependent on. So suppose, for example, I want to know how is the height of river water dependent on the amount of rainfall received in the neighboring areas. So of course, the height of river water is dependent on how much rain that area is receiving. And I want to know at what rate the height of the river water changes uh, with respect to the rainfall received in the nearby areas. So how will I get to know that? I'll get to know that with the help of what is called a derivative. So I'll calculate the derivative of the function which describes the relation between the height of river water and the amount of rainfall, and whatever quantity I'll get will be the measure of the rate of change of the height of river water with respect to the rain received in the neighboring areas. Now, that was pretty much the idea of a derivative. Now, what is a partial derivative? So, continuing the same example, one may argue that the height of river water is not dependent on only one factor, that is the amount of rainfall received. It can be dependent on various other factors like uh, the the amount of water released by a nearby dam, or the amount of ice melted, or maybe you can call the temperature at the mountain regions. And in that case, suppose I want to know that how much of any one factor independently affects the height of river water. So I've been given a relation which tells me, okay, this is the height of river water and this is how it's dependent on all the three quantities. I have a relation, suppose x minus y plus z. And I want to know that how much, what is the rate of change of the river water with respect to only one factor, like suppose the water released by a nearby dam. So how do I know that? So again, the partial derivative is the tool that we use in this case. And what the partial derivative does is that it will tell you the rate of change of the given quantity with respect to the quantity of interest, by keeping the other quantities constant, like ignoring them. So yes, that was pretty much the idea of partial derivative. So if I calculate the partial derivative, in that case, I'll get the rate of change of height of river water with respect to the amount of water released by a nearby dam, ignoring other factors like rainfall or temperature in that case. So that was the idea behind it. And now we'll look at the maths. So as you can see on your screen, you can consider a function f of x comma y is equals to x plus y. So first of all, how do we know that what are the variables that the function is explicitly dependent on? So this bracket next to f that says xt comma yt. So whatever variables are written inside the bracket will be our independent variables. So in this case, the independent variables are x and y, but we can see that even x and y are not completely independent. Like x is dependent on t, y is dependent on t again, and we can relate them by using the relation 3x equals 2y. But we have to treat them independently because that's how our function is defined. That's how we state the function to be. The partial derivative of f with respect to x treats the variables as independent, and it will fix y while only varying x regardless of how they may be related. So we don't have to consider that, okay, y x is dependent on t, y is dependent on t. So we are not going to write it as xt plus yt is equals to 2t plus 3t is equals to 5t. No, because that's not how our function is defined. We have to consider x and y as independent variables. So suppose I want to find the partial derivative of f with respect to x. I am not going to write this as 2t plus 3t is equals to 5t and then calculate the derivative with respect to 2t. No, that's not how I am going to do this. Uh, However, that will be the case if the function would have been f of t, as you can see in the third last point from the bottom. If it would have been f of t, that is the independent variable in that case defined by the function is t. So we'll write the function as 2t plus 3t equals to 5t and then take the derivative with respect to t, and that will be 5. So that's how partial derivative works. So suppose for the above function only f of x comma y, I want to find the partial derivative with respect to t. So the partial derivative of this function with respect to t will be 0. It might feel weird, but it will be 0 because again, the function does not specify t to be an independent variable. It is only specifying x and y to be the independent variables. So we are not going to write it as 2t plus 3t equals to 5t and calculate its derivative with respect to t. The derivative of the function f of x comma y with respect to t will be 0. Uh, so this was for partial derivatives and how they work, but regular derivatives do not work that way. So and they allow for variation of other variables as well, and we use the chain rule in that case, which has been mathematically expressed in the below picture. Now, moving next to the Newtonian picture. So before looking for alternatives for the Newtonian mechanics, we'll first try to understand what the Newtonian picture has to offer. So most of us would be already familiar with how Newtonian mechanics works and what is it in essence. So first of all, the motion of point particles is described as position varying over time. So our main goal in Newtonian mechanics is generally to track the motion of the particle and find a relation which tells us how the position of the particle is varying over time. That's pretty much the goal of solving our problems when we are using Newtonian mechanics. And the position of a particle can be mathematically expressed using coordinates. So suppose I want to know the where is the particle. So I'll use some coordinates which will tell me that okay, your particle is here. So we use the XYZ coordinate system, for example. And each coordinate consists of a value and a corresponding action to be performed. So suppose my value of my x coordinate is 5. So what action is related to it? The action related to it is that I'll move in the x direction, and that is where my particle will be situated. And we also define useful physical quantities that appear in several relations or are conserved in many situations. So these physical quantities are like momentum, angular momentum, energy, and we'll see that how these quantities help us to solve problems and how they are important. Next, Newton's laws give us mathematical relations between the coordinate values and their derivatives with respect to time. So, for example, Newton's the second law, F is equals to ma, gives us the relation between the force. So, first of all, what is a force? Force is the influence acting on a body which is causing motion. And force is equals to, so it relates force to acceleration. And what is acceleration? Acceleration is nothing but the second time derivative of position, d2x by dt square. So Newton's laws gives us this mathematical relations between the coordinate values and the derivatives with respect to time. And in these relations, our quantity is called force, which I mentioned that is nothing but an influence acting as a cause for a particular change in coordinate values, as described by Newton's second law. And then there are second order differential equations in the coordinate values, which when solved and provided the required initial conditions, allow us to predict the future motion of the particle. So those who are familiar with the concept of differential equations might know that when we are given a differential equation, we solve it and we get a general solution. But to get the exact solution, we need some initial conditions. When we plug in those initial conditions, we get the exact relation governing the motion of the particle or the behavior of the system. So that was a Newtonian picture for you. And of course, mechanics formulation of such great vastness will of course have some achievements. And what are those achievements? So coming on to that, Newtonian mechanics allows us to develop a consistent theory of systems of particles using concepts like the center of mass. So the second law of motion, if you must have known in detail, states that the net external force is equals to mass times the acceleration of center of mass. So the Newtonian mechanics introduces us with the concept of center of mass, which helps us easily solve problems where the body in question might not be a point particle, it can be a rigid body with large dimensions, and hence, and in those cases, we use the concept of center of mass to basically ease our problems. Newtonian mechanics then helps us to prove several well-known results like conservation of linear momentum, conservation of angular momentum, as well as conservation of energy mathematically. So, for example, I'll take conservation of linear momentum. So we know that linear momentum is conserved when there is no net external force. So how do we see that mathematically? So we know that the Newton's second law can be written in the momentum form as F is equals to dp by dt, where p is the momentum of the particle. So if net external force is equals to 0, so dp by dt is equals to 0. That is the rate of change of momentum with respect to time is 0. That is the momentum is not changing with time. That is the momentum stays constant, and that is what is conservation of linear momentum actually about. And same goes for conservation of angular momentum. Net external torque equals 0, angular momentum is conserved. We can see it with the torque equation. And like that, Newtonian mechanics provides us with ways to prove these well-known results. Then Newtonian mechanics is useful for solving problems involving simple systems and can provide solutions even when dissipative forces are acting. So for example, if I know the nature of a dissipative force, like friction, we know how it works. So I can use Newtonian mechanics to solve these questions. Then it is mathematically simple, of course, and it does not require knowledge of high level mathematics to understand, and is thus an ideal introduction to classical mechanics. So if you're going to go through classical mechanics for the first time, obviously you start with Newtonian mechanics. You are not going to dive deep into straight away Lagrangian or Hamiltonian mechanics. So yes, it's mathematically simple. Moving on next, I mentioned some conservation laws like conservation of angular momentum, conservation of linear momenta. So how are these conservation laws important? So what these conservation laws do and how they are generally important while solving problems is that they simplify our calculations. So suppose if I know that momentum is getting conserved, I can straight away conclude, okay, no net external force, no net, and if no net external force, then no net acceleration of the center of mass. If no net acceleration of center of mass, then second derivative of position with respect to time equals zero, and I can work my way out if I know some conservation law is being applied. They eliminate the need to solve complex differential equations. So suppose there would have been the net external force, and again I'll take the momentum example. So suppose the net external force would not have been zero, then F is equals to ma would be some like m d2x by dt square is equals to some weird expression which tells us about the force. Then we would have to solve a second order differential equations, which might not be easy in every case. We can solve it obviously, but it might not be easy. And if I am given a conservation law that is being applied, then my work gets easy to do. Next, these conservation laws are often transferable among fields in physics. That is, any conservation law that is applicable in classical mechanics, it is going to be applicable in other fields of physics as well. That is optics, etc. Now, moving on to the issue with Newtonian mechanics, why do we want to look for alternatives? Of course, every coin has two sides, and same goes for Newtonian mechanics. There are some problems that we face while solving questions, and one of it is that oftentimes we face the problem of resolving forces, velocities, and positions into components. So it is by experience you must have known that resolving everything in multiple components, is not a very easy task to do, because even after you resolve them in components successfully, you will have to solve the equation separate. You'll have, suppose there are n different components, you will get n different equations, and you'll have to solve n different equations separately. So it's again a very tiresome job doing all that work, especially in the case of complex systems like the double pendulum, as we'll see in the for the slides. And in those cases, we observe that working with forces is not a very good idea, and we see that energy might be a better idea to work with. So suppose I am studying a spring block system, and a spring block system in one dimension is easier to do because of course there is no need to resolve them in components. But if I want to study a spring block system in 3 dimensions, then it can be problematic for me because I would have to resolve the forces again in 3 components, the velocity of the block in 3 components, namely the XYZ component, and the acceleration as well in 3 components. Then solve all these equations, then compile whatever you got, and then you get the solution governing the behavior of the block. However, if I want to calculate the potential energy stored in the spring, I can straight away measure the extension of the spring from its natural length without worrying about its extension in the x direction, y direction, and z direction. I just have to calculate the extension in the spring length, and I am with my answer. What is the potential energy stored in the spring? Same goes for kinetic energy of the block. I don't have to worry about the x component of velocity, y component of velocity, z component of velocity. I just have to worry about the net velocity, that is vx square plus vy square plus vz square, and that can be measured without resolving into the components. Next, although conservation of quantities can be proved in a post facto manner, the theory itself provides us with no means aside from randomly guessing whether a quantity could be conserved or not. So, although we can prove conservation of linear momentum and angular momentum, but there are some quantities in some complex systems that by looking at the system, we might not be able to tell directly, okay, this quantity is getting conserved. Okay, that's how it works. There are some you see very out of the box quantities getting conserved that you will not see anywhere obviously that, okay, this is getting conserved. So that is again another problem. It makes again the problem complex. It also does not give a complete understanding of why some quantities are conserved while others aren't. And Most importantly, it is not generalizable to provide descriptions of particles in other fields of physics. So Newtonian mechanics fails in other fields of physics. It is not generalizable, which is a very bad thing for for any mechanics formulation. So now, since we have been introduced with what is Newtonian mechanics, how does it work, when does it work, and when does it not work, I think it would be okay to say that, okay, Newtonian mechanics, we don't need you now. Of course, we deserve better, and we can throw Newtonian mechanics in a fireplace as of now. And we are good to go with some other alternative that helps us do things in a better way and does not give us the trauma of resolving into many components. So, how do we make it better after Newtonian? What are our alternatives and what do we do? So, on that, I'll hand over the mic to my co coordinator Harsh, who will explore about is energy the answer?
All right, so hello guys, my name is Harsh, and I too am a coordinator of Horizon, and I will be continuing the lecture next. Okay, so my friend Aditya here has told you about how there are problems we face when dealing in Newtonian mechanics. So here comes the question: how do we actually make it better after Newtonian? Well, to make it better, we would have to think beyond Newtonian and more into what is actually fundamental. Because forces are not fundamental, and that's what Newtonian deals with. Which leads us to a question: is energy the answer? Actually, energy as a function of velocities and position is often much easier to calculate than the forces acting on a system. For systems with one parameter and its derivative, provided energy is conserved, we can find the solution through energy methods pretty easily. However, when dealing with systems of multiple independent variables, or when energy is not conserved, energy alone is not sufficient to find the solutions. And so we needed a new method from which we can generalize the use of energy for systems with multiple variables and constraints, which opens up the door for us to some mechanics through the eyes of Lagrangian. Before Lagrangian, though, I would first like to introduce a quantity called action, represented by S, and its value is equal to integral of L dt, where L is the Lagrangian and its value is kinetic energy minus potential energy. Now, why is this quantity called action so important? Well, to make you understand the significance of action and enter Lagrangian, I will tell you a very interesting and my personal favorite concept. Well, to summarize, our universe is pretty lazy and intelligent. For example, light travels in a straight line, and we obviously know that the fastest path for the light from A to B would be the straight path. I mean, we all know if it bent in between, the size of path would increase, and so would the time taken. Now, second scenario, the point B is in another medium. The light will start moving in a straight path, but not towards B. And when switching the medium, it bends towards B and reaches it. And well, guess what? This was the fastest path light would have taken to reach B. So, how did the light know this path to take to reach B? Or actually, did light only take the path we saw? Today, we can easily say light bent because of the change in refractive index. But what if I told you to predict the path of light, or actually anything? There is a simple principle that the universe follows. And here introduce the very interesting and simple principle called the principle of least action. Principle of least action states that the path taken by a physical system between two states at two different times is the one for which action is minimum. Now, as I have said, we can find the path of objects with this, but how? Well, by just extremizing action to be the minimum, for which I would first have to teach you about variational calculus and how to extremize a function with it. Well, variational calculus is a pretty simple field of math where instead of finding numbers to maximize or minimize a function, we find a function to maximize or minimize a function. And you can see an example of a function here. It is basically a function is basically a function of functions. And the function we are concerned about in this case is action, which is the integral of L dt. And L depends on yt, which is a path, y dot t, which is a velocity, and t, which is our time. Now, how do we actually extremize it? Well, yt would be the function which will extremize this. And so we make a small change in yt, taking the epsilon a small parameter. an NT an arbitrary differential function such that NT1 is equals to NT2 is equals to 0. If we input this new by t with a small variation into the original equation and differentiate it with epsilon, and then upon further simplification by using integration by parts on the second term, we can find that we would get delta s is equals to integral of t1 to t2 of del L by del y minus d by dt of del L by del y dot into nt dt. And upon further simplification by using the property you can see on the screen, where because of nt being 0 at the at the endpoints, the function we have in the bracket would be equal to 0. And we would get a double differential equation, second order differential equation, dl by dy minus d by dt of dl by dy dot. And when this equation is a very important second order differential equation, which is also known as the Euler-Lagrange equation. Now I should probably show you how is it even usable in an example. So let's take a simple example of throwing a ball at an angle theta with the horizon with velocity v naught. Well, to solve it, we can just easily calculate the Lagrangian for it, which is, as we know, kinetic energy minus potential energy, and then solving for the x direction and the y direction in separate places. If we do that, we get the acceleration in the x direction and the y direction. And upon integration of those, we would get the path. We would get the equation for the path the ball would take, which is basically the equation of motion. And we found those using Lagrangian this time instead of the force-based view we do in Newtonian. Well, as you can see, this is all possible because of Lagrangian. So we will now move on to Lagrangian. But first, for it, I would have first have to teach you some basics about coordinates. So bear with me till then. Okay, so generalized coordinates. Well, you definitely know about the Cartesian coordinate system, but that is not the single coordinate system there is. In fact, we can make our own coordinate systems. So here comes generalized coordinates. It just needs to follow three simple properties. First, each coordinate must be independent of one another, and we can simply check it by varying one of the coordinates and keeping the other constants. Second, all aspects of the particle must be described completely by the set of coordinates and the time derivative of any order. The third, there must exist relations which allow us to solve for the motion of the particle expressed in these coordinates. Now, coordinate system following these three properties would be a generalized coordinate system. By the way, if as you can see, we have not said if the coordinate would be angular or linear. So there is no constraint upon that, and we can choose on our own. But if there are any other constraints, we will have to choose coordinates which satisfy these constraints. And from there, we come on to Lagrangian formulation of classical mechanics. By the way, since we have learned about generalized coordinates, we won't be talking displacement, velocity or force, but instead generalized coordinate, m derivative of generalized coordinates, which I will be calling generalized velocity here, and generalized forces. So here in Lagrangian formulation, instead of using forces, we use energies to derive second order differential equation. There is just a small condition to follow, that the coordinates and their time derivatives must all be continuous, and that there must exist a potential function from which all forces acting on the body can be derived. Now, good for us, we have actually derived the second order differential equation before when we were learning about action. This time, it's the only difference is that it's in generalized coordinates and the generalized velocity. As you can see, the qj is a generalized coordinate and the q dot j is a generalized velocity. Now, as we have seen generalized coordinates and generalized velocity, as I've said, there is also something called a generalized force. Well, generalized force is a culmination of all the forces being applied, and we can calculate the component we want using appropriate generalized coordinates. Like how we used to know that negative or partial derivative with respect to x of potential function would give us the x component of the force. Similarly, partial derivative of potential function with respect to any generalized coordinate will give us the generalized force. for that coordinate. Now, an example of this would be if the generalized coordinate is angular, the force we would get would be a torque. And as it is for the case of force, we also have generalized momentum. And same as force, when the generalized coordinates are angular with respect to some axis, we would get angular momentum from this. And the uh, generalized momenta here is the partial differentiation of Lagrangian with respect to the generalized velocity. Now, I have shown you a simple example of how to use Lagrangian for a ball thrown in an angle theta. But well, that's pretty simple. Everybody can do it, even using Newtonian. So now we come on to a more complex situation. First, let's see what a simple pendulum is. Yeah. So as you can see, this is a simple pendulum as we all know it, and it's pretty simple as the name suggests. But there is actually a more complex counterpart to it, and it's the double pendulum. I hope you can see it clearly. Well, the double pendulum, as you can see, its motion is well chaotic to say the least. And can you imagine finding the equation for the endpoint of the second rod using forces applied, the velocity and everything? So it's basically practically impossible solving this when using Newtonian mechanics. But if we use Lagrangian, it's a different story. It's practically a breeze now. This is solving of double pendulum. If we are considering two bobs of mass m1 and m2 using Lagrangian, we simply have to find the velocities for it, and that is pretty simple. And then finding the Lagrangian for it, which is the kinetic energy minus potential energy, and we can easily get the motion of varying theta 1 and theta 2. And if you want to simplify it even further, we can consider small oscillation and a small angle approximation, and then we'll get these two equations, as you can see, 6.212, and it was pretty simple to find them. Unlike what would have been if we tried to solve it with Newtonian. Now, moving on, we come to a new concept and a great theorem, which even helps us in proving of conservation of linear momentum. In Lagrangian, as we saw, we describe a system with generalized coordinates. Now, if a generalized coordinate does not appear explicitly in Lagrangian, it is called a cyclic coordinate. And of course, Lagrangian's partial derivative with respect to that coordinate would be equal to 0, meaning the generalized force would be 0, which leads us to believe that generalized momenta shall be conserved. Now, what does Noether's theorem state? Well, if the action of a system is invariant under continuous symmetry, then there exists a conserved quantity. And what is a symmetry? Well, if you do a transformation of a system and it leaves the physical systems, physics, meaning action or Lagrangian unchanged, then there is a symmetry. So I'll give you an example. Suppose you rotate your coordinate system and the Lagrangian doesn't change. That means the system is symmetric under rotation. And as another theorem state that if there is a symmetry, then there must exist some conserved quantity. And now it's pretty easy to visualize. Now, let's consider a particle moving in a 3D space with mass m. Now, there is no external force here and no potential. And a generalized coordinate would be x, y, and z. The Lagrangian in this case would be half mx dot square plus half my dot square plus half mz dot square. Now, does this Lagrangian depend upon x, y, or z? Well, as you can see, no. So, if we were to change the position of the system, would there be any effect on Lagrangian? And the answer is same, no. So, which means that the partial differentiation of Lagrangian with respect to these generalized coordinates would be equal to 0. And so, there is a symmetry, and so is a conserved quantity. And upon simply using Euler Lagrange equation, we get the quantity, which in this case, would be the linear momentum. So, as you can see here, we just proved the conservation of linear momentum. But what about conservation of energy? Well, let's say Lagrangian does not depend on time. Now, if we take the derivative of Lagrangian and then using Euler Lagrange equation, on simplifying the equation, we would get this function as you can see in the bracket. Well, this function is actually pretty important and is actually the energy function H, which represents total energy of a system and is defined in Hamiltonian. Now, moving on, we have so far described motion using generalized coordinates, and we use Lagrangian, which depend on coordinates and the time derivative. Well, Lagrangian gives us n second order differential equations. Each second order equations meet two initial conditions, typically which are position and velocity. That means we need two n initial condition to solve the system. But we thought instead of solving n second order equations, we can split each one into two first order equations, leading to two n first order equations. Now, to switch to this first order framework, we will need to define two n variables. And now, which would be the generalized coordinate, and the other end would be the generalized momenta. And these generalized coordinates and general momenta are actually called canonical variables. But we all know that Lagrangian actually doesn't deal using momentum. So we need to construct a function that takes these canonical variables directly. And so we shift to Hamiltonian, which uses generalized momenta and generalized coordinates directly. And to construct this function from Lagrangian, we use Legendre theorem, Legendre Transforms. Sorry. Now, this new function that we just made exists in a mathematical space called a phase space. And now my co-coordinator Aditya will once again continue on the lecture from the topic of phase space.
So, what is a phase space? So, again, simply stating that phase space is another way to study the motion of the particle, another way to track the dynamic of a system. So, suppose we plot position time graphs, we plot velocity time graphs, we plot acceleration time graphs, and we get some information about how a body or a particle in study behaves. So, similarly, in a phase space, we generally plot momentum versus the position or angle or whatever the generalized coordinate will be. So we plot the momentum versus position in a phase space, and we try to study the dynamics of the system. So each point in a phase space then in that case corresponds to the unique state of a system. So first of all, I'll go through the formal definition of phase space. So a phase space is a mathematical space that represents all possible dynamic states of all possible states of a dynamic system. It's a way to visualize and analyze. It's a way to visualize and analyze how a system changes over time by plotting its state variables, which can include position, momentum, or other relevant parameters. So we study generally the geometry of this phase space graph that we are plotting. So these arrows that you see are nothing but they tell us the flow of time. So suppose I am at any given xyz point on the circle that you see. So this arrow tells us that as time evolves, how will the state of my system increase, that how will the momentum increase, how will my angle or position change. So that is how we use phase space to study the dynamics of a system, to study the behavior of a system. And as I mentioned, it is to be noted that time t is not part of a phase space. It's an intrinsic parameter, not a coordinator, not a coordinate. So the evolution of time is again indicated by these arrows, and time is not a coordinate here. We can, however, see the evolution of time by these arrows. So, specific geometries of phase space tell something special about any system. So, suppose a phase space which has a closed curve like this circle or this ellipsoid type shape, this tells us that some quantity of the system is getting conserved, and this quantity is nothing but energy. And you may observe that when we plot the phase space for a spring block system, we obtain something like this one, something like an ellipse. And that is how phase space helps us to study the motion and behavior of any given system. That is how phase space is useful. Now, we mentioned in the last to last slide that we need to change variables in order to reduce our differential equations. And so how do we do that? So we see that so first, making clear our objective, what our objective is that we want to replace replace the generalized coordinate with its derivative. So suppose I have a function f of x comma y comma z. So instead of writing the function as being dependent on x comma x y or any or z, I want to write the function being dependent on rather the partial derivative of the function with respect to that coordinate. So suppose I want to eliminate x, I want to write the function in this transformation as f of del f by del x y comma z. So that is pretty much the objective of making a change of variables. We want to do a one-to-one mapping from the xy coordinate space to the slope intercept phase, and we'll see how we can do that. And one may say that an obvious method to do that is to calculate the partial derivative with respect to x and then eliminate x, plug in into the original equation, and then we get the function f in terms of its derivative. But that is not a wise thing to do because we lose some information while doing that. So uh, on the top left corner of the screen, you can see a function which has such kind of a graph. So when I do the partial derivative and plug it in the original equation, what I get is something like the function on the right. Like I get a family of curves because if you see the derivatives at any given point, the derivatives for all these three curves will be the same. Like it's not different. We are losing some information about the y-intercept, and hence it is not a wise thing to do. And how we can avoid this situation is by using another tool called Legendre transformation. This is a special transformation that we'll use to avoid that situation. So again, to get a graphical idea of what that means, so think about it this way. I have a graph and I have information about the graph stored as coordinates. Like, okay, these are the coordinates from which the graph passes. So I want to use the same information and store it in some other way. So what can be a good way to do that? So if you think about it, every point in a curve has a unique tangent. And if there is a unique tangent, so every tangent line will have its unique equation y is equals to mx plus c. And these m and c will be unique for each tangent. So for each point, I have a unique tangent which will have a unique equation. So if I somehow somehow find a relation which stores the information about these slopes and intercepts of all these tangents at all these points, then I can I can I'm basically successful in storing the information in a different way. All the information that was there in xy coordinates is now stored in the form of the slope and intercept of a given tangent. Now, again, Legendre transformation is the tool to do that. And it's a coordinate transformation that preserves the information. And it works on the fact that an equivalent representation of a function in one variable can be obtained using the slopes and y-intercepts. As I mentioned again, each point has a unique tangent. Each tangent has a unique equation. Each unique equation will have unique values of both slope and intercept. So if I find a relation between the slopes and intercepts, I am I am again maintaining the uniqueness of the point and storing the same information, but in a slightly different way. So, of course, when can we do Legendre transformation? We cannot always do Legendre transformation, and there are some specific conditions under which I can do that. But we may not need to be much concerned about that because Lagrangian, that is a function of interest, satisfies these properties for most of the cases. And the output of the Legendre transformation of the Lagrangian, that is when we apply Legendre transformation on our Lagrangian function, we obtain something called Hamiltonian, which is another very important quantity and which is the fundamental for another form of mechanics, Hamiltonian mechanics, that we'll study in the next slides. And and what is Hamiltonian? Hamiltonian is nothing but T plus V, where T is the kinetic energy of the body and V is the potential energy of the body. And it is pretty much same. It has the same form as an energy function as we know it. Now, moving on, why does it work and what are the conditions that are necessary for Legendre transformations to be applicable? So the function should be a strictly convex differentiable function. So what do we mean by that? Is that the first derivative of the function should be a strictly increasing function. That is, for all x2 greater than x1, the function px2 should be greater than px1. And it should be differentiable, that is, its first derivative should exist at all points. And when we apply Legendre transformation, we are expressing the function in the form as it's written, f star is equals to f minus xp. And if I apply Legendre transformation on this function again, I get the original function once again. So that means on inversion, I am able to reconstruct the original function again. That is, my objective of preserving the information and storing it in some different form is satisfied. I was successfully able to convert the information in some different form, and which is representing the same thing that we were representing using the earlier function. So thus no information has been lost during the transformation and the variables have been transformed, and such a transformation is what is called Legendre transformation. Now, taking on to the further slides, I'll invite Nanta and he'll continue the session from here.
Yeah. So hello everyone. I'll be picking up from where my co-coordinator has left. So let's look into what cyclic coordinates are and some information about Legendre transformations. So when do we consider a coordinate to be cyclic? So basically, it turns out that a coordinate is considered to be cyclic if the partial derivative of the Lagrangian with respect to the said cyclic coordinate vanishes. This basically says that the Lagrangian has no explicit time dependence on the coordinate. So this leads to an important observation that the canonical momenta of the associated with the cyclic coordinate also gets conserved. So this is an important point to note, as this basically gives us some information on how canonical momenta and cyclic coordinates are related. Also, the time derivatives of cyclic coordinates need not be conserved. And why cyclic coordinates now, you may ask? So basically, what cyclic coordinates do is cyclic coordinates basically reduce the number of independent variables, and which basically reduces our the complexity of the problem. It sort of trivializes the problem in a sense. So we would like prefer to look into the system or the problem in terms of cyclic coordinates and their conserved canonical momenta instead of time derivatives and the cyclic coordinates. So this is a powerful tool to simplify the system and look into its solutions. So we do this by doing Legendre transformation for these variables alone. So so as you earlier seen, the Legendre transformation of a Lagrangian basically gives us the Hamiltonian, as we can see in the equations shown below. So what is the difference between Lagrangian and the Hamiltonian formulation? So in Hamiltonian formulation, we basically look at the system in terms of two and first order equations of motion, whereas in Lagrangian we have n number of second order differential equations. So how do we get these two and first order differential equations which define the motion in Hamiltonian? We do that by taking a derivative of h, and as we can see here, we basically do some clever math, and we get the first order differential equations of in the Hamiltonian space. And moving on, let's see what a canonical transformation is. A canonical transformation basically is nothing but just a coordinate transformation from a set of initial coordinates to a set of final coordinates. But it turns out that they have to maintain a specific condition. That condition being that the equation, Hamilton's equation of motion, must have its form preserved. This is basically the equations which we earlier saw, the first order differential equations. Their form must be preserved during a coordinate transformation for the set transformation to be canonical. So we can also construct varied Hamiltonian which is valid in this coordinate system. As we've earlier seen, canonical transformation is basically just a coordinate transformation from initial set of coordinates to a final set of coordinates. So how do we link these two coordinates? So we basically can introduce a function called a generating function. This generating function basically maps the initial coordinates and the final coordinates to each other. And this sort of kind of generates the transformation itself, you can say. And this generating function, as I said before, has informations on the relations between the old and the new Hamiltonian, old and the new coordinates, etc. And since no information is technically lost during these transformations, if we have the relation between the final and the initial coordinates, the momenta and the Hamiltonians, we can basically reverse engineer to find the generating functions themselves. So this basically just points out that they completely determine each other and they're theoretically invertible mathematically. Moving on, let's define a generator formally. So basically the integrand which we see here is basically just Lagrangian being substituted with Hamiltonian in the Hamiltonian's principle of least action. And this integrand has a solution as shown in the slides. And we set lambda equal to 1 in this solution, as setting lambda equal to some other constant is basically just a scaling transformation. And we can just do that later on. We just set lambda equal to 1 for the purpose of simplicity. And it is very important to note that the solution, the form of this solution, as it is helpful and recurring in the future slides. So next we see also generating functions basically are of four standard forms based on the based on how they map the initial and final coordinates, or how the mixture of initial and final coordinates are present in the generating function. So what do we do? So we basically substitute the generating function f1. With f1 here means a type 1 generating function. We substitute this into the solution for the integrand which we have seen earlier. We expand the material derivative into partial derivatives, and we basically bring the similar terms. We group the similar terms together and match their coefficients on both sides. This leads us with a set of transformation equations. As we can see, these transformation equations basically extract the information out of the generating function on how the initial and final coordinates are to be mapped. Also, we can make an interesting observation that k equal to h plus del f by del t. Basically, this is a very important observation, as it says the explicit time dependent part on the generating function only contributes to the new Hamiltonian. These do not contribute in the coordinate transformations themselves. They do not contribute to the transformation equations, basically. So this is a very important and interesting observation which we can note. Also, K, the new Hamiltonian, can be called as a Hamiltonian. It is just a name given to the new Hamiltonian. New Hamiltonian. And as I earlier said, these are completely equivalent. We can basically reverse engineer to get the generating functions out of the initial and final conditions. So that is what we can. That is also something we can do, and which is shown in the slides. As I've earlier said, this f1 basically the explicit time dependent part on the generating function do not affect the equations of transformation. They only affect the final Hamiltonian, the Hamiltonian itself, and that is what is being stated here. Also, we can choose the generating function as a mixture of any old and new variables, which is an interesting thing to note. And also, we can convert the generating function of a certain form to another form using Legendre transformations, where we basically change the combination of the old and new variables present in the generating function. Also, as I've earlier talked about some standard forms of generating function being present, we can use a mixture of all these standard forms as long as to define a generating function, as long as there are two independent parameters. This can also be done by using the Legendre transformation again. So now let's look into some types of transformations, canonical transformations. So let's start with the most trivial canonical transformation, which is the identity transformation. So as the name itself says, the identity transformation does basically nothing. It just maps the initial to final coordinates with no change in the coordinates itself. coordinate relations itself. And we can we need not spend much time into this, and we'll be moving on to another type of transformation called the point transformation. Now, this sort of a broader subset of the transformations itself, and let's see how the point transformation is defined. So basically, the point transformation is defined such that the new position coordinates are only dependent on the original position coordinates, with no dependency on the original momenta coordinates, etc. So this is what point transformation is defined as. And also, it turns out that the final momentum coordinates need not be only dependent on the initial position coordinates, and in turn, they must be dependent on the original position coordinates and the original momentum coordinates. I'm talking about the final momentum coordinates here. Also, these type of additional constraints in the transformation lead to f being invertible independent, and this is why we can express the initial coordinates in terms of final coordinates explicitly. Now let's move into another type of transformation. Here you can clearly see that the initial position coordinates is replaced with the final momentum coordinates, and the initial momentum coordinate is replaced with the final position coordinates. So basically, we just exchange the coordinates themselves, and this is defined as a exchange transformation. Also, it is very important to note that Qi and Pi here, there's no concept of Qi being a spatial coordinate and Pi being momentum, mass times velocity. They're just abstract basis vectors in the phase space, which we used to define the Hamilton formulation. Now, let's look into exchange. Okay, so yeah. Now let's look into exchange transformations and how they work. So basically, we have already seen how exchange transformations are defined. They basically are just interchange between the coordinates, initial momentum and the final position coordinates, and vice versa. And as I've earlier said, there can be generating functions of mixed nature. And we see one such example in the slide which I'm presenting right now. And we also know that the generating functions can be transformed to another form using Legendre transformations. We basically do that here. And we basically follow the same procedure which we followed earlier to get the transformation equations. And we also end up with a set of transformation equations for this system. And moving on, let's solve an example using canonical transformations. Here we solve an first degree SHM oscillator using the canonical transformations. The Hamiltonian of the said SHM oscillator is defined as such. And this is just basically math. We have some relations between the initial and final position coordinates and momentum coordinates, the Hamiltonians, etc., given defined in the question itself. And here we basically divide the initial position and momentum relations to eliminate f of p, and we reverse engineer the initial and final data which is presented to us to find the generating function. And once we find the generating function, we can basically find the new Hamiltonian, the Hamiltonian. We can basically find the position coordinates, etc., frequency, everything. You can just find explicit, clear solution for the system. Yeah. So okay. So now let's look. We can say, so we're just doing a coordinate transformation. Why do we need to introduce a generating function as an intermediate step which maps the initial and final coordinates? Why can't we just define the coordinate transformation based on the relations between the coordinates and the Hamiltonians alone without using a generating function? You may ask. I mean, just we can do that, and we'll be seeing how to do that here. And this is the idea behind symplectic formalism. And it's also important to note we shall be only considering restricted canonical transformations from now on. So what a restricted canonical transformation is basically that we basically have no explicit time dependence in the generating function. The coordinate transformations do not depend on time explicitly. That is what a restricted canonical transformations are. And we'll be looking at the restricted canonical transformations in the symplectic formalism from now on. So before moving on, let's look into something called a Jacobian, which is pretty important. So the Jacobian is nothing but a transformation matrix. This transformation matrix has information on how the initial and final coordinates are mapped. And mathematically, the Jacobian, the transformation matrix M, is defined as the partial derivative of zeta with respect to eta. Here, zeta being the final coordinates and eta being the initial coordinates. So it's basically the partial derivative of the final coordinates with respect to the initial coordinates. Also, the determinant of the Jacobian basically uses the ratio between the differential volumes of the new coordinates and the old coordinates. So they basically say how the volumes are, how the differential volumes change when we do a coordinate transformation. And we also define something called an inverse Jacobian matrix. This basically does the reverse mapping of what the Jacobian matrix does. This inverse Jacobian matrix basically maps, let's say, a coordinate y to x, where the Jacobian matrix defines a mapping of a coordinate from x to y. Also, we can say that the Jacobian of an identity coordinate transformation is just an identity matrix, as the identity transformation is itself is a trivial case of a transformation. So now let's continue with the simplification approach for the restricted canonical transformations, which we have discussed. So we basically define some matrices to simplify the notation. And here eta is basically the set of matrices, which is basically the matrix which which is a set of matrices having the initial coordinates. And rho h by rho eta is basically the partial derivative of h with respect to the initial coordinates. Here J is a peculiar type of matrix. This J is called the symplectic matrix. This basically has information on how the geometry of the phase space behaves. So basically, you can say J basically has information on the geometry of the phase space itself. And we also can say that the geometry of the phase space is in itself symplectic in nature. Also, as you already seen the Hamilton's equation of motions earlier, we basically define a matrix form for the said Hamilton's equation of motion as shown in the slides. So we also have defined what a Jacobian is now. So we use the Jacobian to map the transformation from an initial set of coordinate eta to a final set of coordinate zeta. Here being zeta equal to m into eta, we basically take the time derivative of on both sides, and we end up with zeta dot equal to m into eta dot. And we do the same for rho h by rho eta. We replace rho h by rho eta in terms of rho h by rho zeta, and we get a relation rho h by rho eta equal to m transpose rho h by rho zeta. This can be more clearly understood using indices for some clarity, but we can just do that yourself if you want to. Also, what do we define by a canonical transformations? Let's recall what we define as a canonical transformation. So basically, the form of Hamilton's equation of motions must be preserved for a transformation to be canonical transformations. We already know that, and hence this zeta dot equal to mj m transpose rho h by rho eta. This is the Hamilton's equation of motion in the new coordinates. This must have an identical form to the Hamilton's equation of motion in the old coordinates. This is only true when mj m transpose is equal to j. Now we finally get a relation condition mj m transpose is equal to j. This condition basically defines the canonical transformations itself, and we can also say we can also find that the determinant of m is found out to be plus or minus 1, which says that the differential volume elements are invariant under coordinate transformations, which means the volume elements do not change when differential volume elements do not change when we do a coordinate transformation. And it is also important to note that we are only doing this for restricted canonical transformations, which is an important thing to note. Also, we have earlier said that the absolute value of the determinant of the Jacobian is basically 1 in the symplectic transformation. So this basically says that the differential volume element is invariant under canonical transformations as long as it's a restricted canonical transformation. Now we can construct a larger volume as a sum of several different differential volumes themselves. So doing this, we arrive at a class of canonical invariants called the integral invariance of Poincare. So what this basically says that that finite volumes in phase space themselves are also canonical invariants, as these as in the shown equation. D eta basically represents the differential volume elements in the coordinate system eta. So and by applying the limits of integration, we basically end up with this nice equation which says that the finite volumes in the phase space are also conserved by doing a canonical transformation. This is also an important thing to note. Moving on, let's look into some properties of symplectic canonical transformation. So first, let's consider a canonical transformation from eta to zeta to be symplectic in nature. So this basically means that they satisfy the condition MJ M transpose equal to J, and there also exists an inverse matrix M inverse, and this basically implies that the transformation from zeta to eta are also symplectic as shown in the as shown in the equation 201. And now let's take another case. Let's take a more broader case. Now let's say the transformation from eta to zeta and the transformation from zeta to eta are symplectic. So basically, we have two sets of conditions of mj m transpose equal to j being true for the two set of transformations. Now it turns out that the transformation from eta to zeta and the transformation from zeta to the new coordinate system, since they are symplectic in nature, the final transformation from the coordinate system eta to the final coordinate systems are also symplectic in nature. So this is kind of like the equivalence. This is kind of a equivalence relation. Also, if you know about transitive properties in sets, basically it's kind of an analogy here, where like if a set A to B is transitive, B to C is transitive, a set A to C is transitive. It's just an analogy, which is kind of interesting. So now let's look into what a Poisson bracket is basically. So a Poisson bracket is mathematically defined as shown in the slide. And what does a Poisson bracket say? So a Poisson bracket basically says how physical quantities change when we do a transformation, when we do canonical transformation. Also, it turns out that the Poisson bracket structure itself is a canonical invariant, which means the Poisson brackets do not depend on the canonical coordinates in which we are operating. And we also have defined the Poisson bracket in its matrix form as dou u by dou eta transpose j dou v by dou eta. And we can basically expand this to get the Poisson bracket formulation using indices. Now let's look into some properties of Poisson brackets and Lagrange brackets. So Poisson bracket, basically the Poisson bracket of two similar canonical invariants is zero, and it turns out they are antisymmetric in nature, and also they are not associative. This non-associativity is pretty important, and it's a important point to take note of. Also, we find something called a Jacobi's identity, where we define where we use three canonical quantities and define that the brackets of each individual quantities in order turns out to be the sum of these the sum of these Poisson brackets turn out to be zero. Also, we have mathematically expressed Lagrange bracket using an equation as shown in the slide. This Lagrange bracket, if you look closely, has some resemblance to the Poisson bracket in its structure, where we basically just invert the rho e by rho eta transpose and rho v by rho eta in the Poisson bracket to get the Lagrange bracket. And naturally, there is also a relation between the Poisson bracket and the Lagrange bracket being defined by the set of equations which is shown. Now let's move in. Now, yeah, basically, I'll be giving the mic to my fellow coordinator. Suraj will be taking up the stage from now on.
Yes, so we will now discuss an important part of classical mechanics, which is known as infinitesimal canonical transformations or ICTs. The transformations we have seen till now are finite transformations, but ICTs vary only very slightly from our initial coordinate system. So this new coordinate system zeta is defined as eta plus delta eta, where delta eta is a very small variational term. Since our transformation itself is infinitesimal, it can be expressed as the identity QIPI plus some infinitesimal generator epsilon g, where g is some function of q, p, and t. In a sense, G here itself is the generator of the ICT, not this QIPI plus epsilon G. Because if you see the variation from our traditional canonical equations, the variational terms depend only on G. If you look at these equations over here. So consider the case of mapping, we have seen restricted canonical transformations till now. What if we map eta to some zeta of t with explicit time dependence? The question is, when is this mapping symplectic? Now, zeta of t naught to zeta of t naught plus gt is an ICT. And consider some fixed t naught where eta to zeta of t naught is symplectic. If zeta of t naught to zeta of t naught plus gt is a symplectic transformation, then by the transitive property that we have discussed before, we can add up a series, compose a series of ICTs from zeta of t naught to zeta of t. And when this is composed again with eta of t naught to zeta of t naught, eta to zeta of t naught, we get that eta to zeta of t, which is not a restricted canonical transformation, is also symplectic. So all that is left to prove is that an ICT is symplectic. So let us consider the Jacobian of an ICT, expand it, and evaluate MJM transpose. We get that MJM transpose obeys the symplectic condition equal to J with an error term on the order of epsilon square, which is negligible because epsilon, if you remember, is an infinitesimal parameter. Thus, we get that the ICT is symplectic, and hence these non-restricted canonical transformations are also symplectic if there is a canonical transformation like eta to zeta of t naught, which is symplectic. Till now, we have discussed canonical transformations as transforming one phase space to another. In such transformations, since our problem and the related variables themselves are independent of the phase space being used, the relevant quantities must be invariant of phase space. What I mean is, if you evaluate, say, something like energy in one phase space, we should get the same value of energy regardless of what phase space we use. Thus, functions like energy, which are well defined, are transformed such that the value when evaluated at the initial and the transformed points are the same. However, since the coordinates of the initial and final points need not be the same, there must be a change in the function's form itself to account for the value being the same. However, there is another approach to understand canonical transformations, which is that points in a phase space are mapped to other points within the same phase space itself. This is called the active interpretation of canonical transformations. Now, what are the properties of this? Since we are in the same phase space, functions must have the same form as before. However, since the variables are not the same, the function may have a different value. It is important to note that this is not a true evolution of the system. This AFQP to B capital Q capital P is not the actual time evolution of the system. It is just you can say an artificial evolution which is created by some change in coordinates. Let us evaluate the brackets with the Hamiltonian in a bit more detail. We'll now evaluate the total time derivative of some function of canonical variables u. We expand it and substitute the appropriate bracket relations. If you see q dot I from the canonical equations and p dot I from the canonical equations and substitute them here, we get that du by dt is the Poisson bracket of u and h plus the partial derivative of u with respect to t. Now, what is the significance of this? Let's say you want to find quantities such that du by dt is 0. But you don't know how the individual coordinates vary with respect to time. what you could do instead is evaluate this expression, bracket of h comma bracket of u plus u comma h plus partial of u with respect to t. And if this turns out to be 0, then we know that du by dt is 0. This gives us a method to identify constants of motion. Now let's say u is h in this case. Then the LHS becomes dh by dt. The bracket of h with respect to itself, the bracket of h with itself is 0. And you get plus partial h with respect to t. And this is an interesting result. It states that if the Hamiltonian has no explicit time dependence, it is a constant. It doesn't matter if the coordinates themselves depend on time. As long as there is no explicit time dependence, the Hamilton remains constant. We can substitute u equal to some canonical variables as well. And we can get this bracket relation shown at the bottom of the slide. Now, if you look closely, these are our canonical equations of motion. And this is just another way of representing those equations of motion. This is in turn like a verification that, okay, we are doing something correct till now. Now, remember this form for an ICT, which we derived previously. We can write the same thing in bracket notation as follows, like this. Now, if our g is h and epsilon is dt, then we get that the generated change in the coordinates by the Hamiltonian and dt is the same as the actual change in coordinates over a time interval dt. This d eta and delta eta are the same quantities. But remember, delta eta is not a true physical change in the system by any means. It's just a artificial change created by some canonical transformation. It just so happens that in the very special case of the generator being the Hamiltonian and the infinitesimal parameter being time, this artificial change and the actual change d eta just so happen to be equal. This means that these real changes in the phase space d eta can be thought of as ICTs generated by the Hamiltonian. And thus the entire motion of the system itself can be thought of as generated by the Hamiltonian. Okay, what if our generator is a canonical variable? If we simplify our bracket relations, which we have seen before, we get that if the variable is pi, then delta qi is generated. And if the variable is minus qi, then delta pi is generated. So the result is that under the active viewpoint, canonical variables create infinitesimal translations in their conjugate variable. This is what we call flow in phase space. We have seen that functional values may change in the active viewpoint. Let's now attempt to evaluate their change. We'll represent their change as dou u over here. And if we use some elementary mathematics, we get this bracket relation. Let us apply this to the Hamiltonian and see what happens. We will specifically consider the case where the generator has no explicit time dependence. Now, expanding the Hamiltonian, simplifying to first order, neglecting the epsilon square and higher order terms, we get that the change in the Hamiltonian is 0 if and only if the bracket of the Hamiltonian and generator is 0. However, we already know that the material derivative or the total derivative of g with respect to time is dg by dt equal to bracket of h comma g plus partial g with respect to t. Since g has no explicit time dependence, the bracket h comma g equal to 0 implies dg by dt is also 0, which means g is a constant of motion. This is a surprising result that constants of motion generate ICTs which leave the Hamiltonian invariant. That is what dou h equal to 0 means. In the specific case of G being a momentum being a constant of motion is generating a change in the Hamiltonian, which leaves it actually invariant. It's generating an ICT, which leaves the Hamiltonian invariant. Doesn't this seem familiar? This is actually Noether's theorem in disguise. We know that if momentum is the generator, translations in position or canonical coordinates are generated. And this results in the Hamiltonian being invariant. And if we flip this on the head, because this is a two-way relation, if a certain translation results in the Hamiltonian being invariant, then the corresponding momentum is conserved, is the statement of Noether's theorem, which we have just shown right now, but using the Hamiltonian instead of the Lagrangian formulation. Let us go further. This active interpretation seems to be pretty interesting. Now, if your epsilon is some continuous parameter, say this parameter is alpha, then the relation becomes dou u equal to dou alpha ug. Now we can evaluate another higher order derivative as follows. And here is the interesting thing. Let's say hypothetically, we are able to remove the u from the left and right hand sides. Then the relation we would get is d by d alpha equal to bracket comma g. And d power n by d alpha power n is bracket comma g power n, where this is just applied n times. That is what we mean by power n. This kind of notation is possible because these relations are true for all g, not some specific g alone. Thus, in a real way, in a sense, since it's independent of u, it is the d by d alpha and equal to bracket comma g which are equal. This is called operator notation. And we can write u of alpha as a Taylor series expanded about alpha equal to 0. Just bring the u out and remain in operator notation, and we get this. Now this series is the Taylor expansion for x puff operator g comma alpha. Sorry, x puff operator g times alpha. If you remember quantum mechanics, there is a very similar equation which arises in the time-dependent Schrodinger equation. When we separate the variables to solve for it, we get this relation over here. The only difference is that there is an iota by h bar present. The difference between these is due to the fact that here we use a Lie bracket or commutator, whereas here we use a Poisson bracket. And these terms arise as a result of that. As we get that our Poisson bracket formulation of classical mechanics is equivalent to the TDSE solutions. This is an interesting result which proves that classical mechanics in its Hamiltonian form is widely applicable to various areas of physics. Here is another one, statistical mechanics. In statistical mechanics, we can represent, again, a system in a phase space. We can also define a sort of density in phase space as the number of possible system configurations per unit volume of phase space. Now, here is the interesting thing. Since the Hamiltonian generates motion in phase space, we have a very important result called Liouville's theorem. So consider a differential volume element with some state points present inside. For this point to evolve and with time exit this differential volume, it must first reach the boundary. But when it reaches the boundary, it always moves with the boundary since the Hamiltonian generates motion, and the Hamiltonian bracket, when it acts on identical points, has identical results. Similarly, for a point outside this differential volume to enter it, it must pass through the boundary. But when it reaches the boundary, it always evolves with the boundary. This means that no point inside can go outside and no point outside can come inside ever. as long as we evolve the boundary as well. But wait a minute, we already know that the volume of the differential element is conserved because it's an integral invariant of Poincare. We also know that the number of points inside this volume element is the same. This means that the density of this within this differential volume element is the same regardless of what point in time we are considering. This gives this is the reason why we have this equation d rho by dt equal to 0. But using our bracket formalism, we can expand it as the Poisson bracket of rho and h plus partial of rho with respect to t. A system is said to be in statistical equilibrium if this term partial of rho with respect to t is 0. And this gives us Liouville's theorem, which is the Poisson bracket of rho and h is 0. This is how I'm sure you guys must be feeling right now, but wait for it. There is a very good resolution to all of this stuff. But to do that, we must venture more into the dark side of classical mechanics. As you know, Vader became a villain before he was redeemed. So we have Hamilton-Jacobi theory. We have just seen how, in the case of cyclic coordinates, Legendre transformations coupled with the Lagrangian can give a pretty elegant solution. Wouldn't it be nice if every coordinate is cyclic? I'll do you one better. Wouldn't it be nice if every coordinate and the momentum are constants? Is this even possible? It turns out that you can do this. And a trivial example is when the new Hamiltonian is 0. Then obviously from our canonical equations, we get that both Q and P are conserved. But how do we do this? The answer is a canonical transformation. Let us use our generator formalism and construct a canonical transformation such that the new Hamiltonian is 0. Thus, we have this equation that h of q partial of f2 with respect to qt plus partial t f2 equal to 0. This is called the Hamilton-Jacobi equation. The solution of this equation in f2 is called Hamilton's principal function s. Now, if you look at this, this has n q's and 1 t. So n plus 1 total independent variables, which results in n plus 1 constants of integration. However, if we add some constant to f2, this equation still remains true if the original f2 is a solution. Thus, one of these constants of integration must be a purely additive constant. The canonical equations, however, depend only on the derivatives of f2, which means this this constant's value is irrelevant to the larger system as a whole. We can neglect this and focus on the remaining n variables alone. Now, the theory of PDEs is a bit complicated. We won't go into it in detail. But what you need to know is that the solution for an n, like any nth order or n degree PDE, is that you have n constants of integration which are independent and they can take any value. They are not bounded. So the F2 here, which has a solution S, is not really a singular solution S, but rather a family of solutions. And these solutions are differentiated from each other by a different value of one of these constants of integration or more of these constants of integration. So what we can do is we can choose a solution of S, which gives us very simple canonical equations of motion. And that is what we'll do now. We will choose a solution such that these constants of integration are exactly the canonical momenta in the new coordinate system. Then these equations, which are present at the bottom of the slide, become true. And we can see that not only Pi, but also Qi in the new system become constant. Now, what is the point? This seems almost too good to be true. Well, the thing is we have to invert these equations to get the solution in terms of Q and P. But more so than that, we have to solve the partial derivative, partial differential equation, which is present here. This is an n plus 1. This is a PDE in n plus 1 variables, which is not exactly simple to solve. But in case we get solutions, the final solving of the first order differential equations is very simple. They are just constants. So there is a fruit to all of our efforts in solving these PDEs after all. Now, is this the only thing we can do? No, not really. We can consider the transform momenta to be functions of these constants of integration as well. And if that is the case, we get these other equations where the new coordinates are not constant, but they vary linearly with time. Before we go any further, is there any reason that we use this symbol S? Because we have seen this before in action as well. Is there any relation? Let's take the time derivative of S to find out. And when we expand it, we get the time derivative ds by dt to be the Lagrangian itself, which means this quantity truly is, or at least has the dimensions of action, which we defined previously. However, this is not really useful to solve the problem itself, because to find an actual solution, we need this S. And S is integral LDT, but the constant of integration is not known. So let us solve rigorously the Hamilton-Jacobi equations. Now, this is a bit tedious, but what this basically says is, if the Hamiltonian has no explicit time dependence, we can split our solution S into a time dependent and a time independent part. This reduces the complexity because now we have solved for T and only we have to solve for these remaining Qi. We can also write our canonical equations in terms of this W instead of S. This W has a special name. It's called Hamilton's characteristic function. And this alpha 1 is our constant Hamiltonian because it doesn't have explicit time dependence. So at the bottom of the slide, we have summarized the canonical equations of motion. We have separated time. Is it possible to separate the other variables as well? That is it possible to write S as a function of only Q1 plus a function of only Q2 plus a function of only Q3, so on, and a function of only time? Well, if that is possible, the Hamilton-Jacobi is said to be separable. And it turns out that these are convenient cases because these lead to simple analytic solutions of the Hamilton-Jacobi equations. Whereas otherwise, the Hamilton-Jacobi equations are mostly unsolvable and we must resort to numerical methods instead. So let us solve SHM using the Hamilton-Jacobi equation. We'll define our W. We'll define our momentum using the generator formalism as partial S with respect to Q. And when we solve it, we actually get our traditional solution in terms of sine and cosine as a result of the Hamilton-Jacobi equation. Now you may ask, isn't this a bit excessive for SHM, which we could solve anyways, way easier using canonical transformations or even Newton's law? That is true. But the reason Hamilton-Jacobi is so popular is because it allows us to sometimes solve equations without explicitly finding solutions. What do I mean by that? Before we get into it, we will look into what it means for a system to be periodic and what kinds of periodicity is there. To do this, we will define something called an orbit in phase space. It is just the trajectory of a system in phase space over time. Now, in periodic motion, what we actually, when we say periodic in this case, what we mean is periodic in the phase space, which is not necessarily in physical space, just in the phase space. So if P and Q are both periodic, then this kind of motion is called libration. For an example, SHM is a case where both P and Q are periodic. Another kind of motion is where P is periodic, but Q is not. And P is a periodic function of Q. For example, consider a plane rotation. the angle variables keep increasing while the system itself returns to its original state after 2 pi radian rotation. This kind of motion is simply called rotation. The constants in the constants of integration in the Hamilton-Jacobi equation are called action variables. And we have seen previously that the conserved momenta are treated as functions of these. However, now we wish to construct new action variables which are designed to replace our constants of integration and our conserved momenta. So how can we do this? Firstly, we shall assume that the Hamiltonian has no explicit time dependence, and for simplicity, we will consider the 1D case. We will define our action variable as j equal to integral pdq, where the integral is evaluated over one complete cycle of q. We can define our conjugate angle variable as the partial of w with respect to j, as before. We can invert the Hamiltonian's dependence on p and q to get p as a function of the Hamiltonian and q. But remember, the Hamiltonian is a constant. And since we evaluate the integral of p dq over one complete cycle of q, the value of the integral itself depends only on the Hamiltonian and not on q. This, when inverted, gives the Hamiltonian as a function of j, which is equal to the integral alone. Thus, the Hamiltonian has no explicit dependence on our conjugate angle variable, which results in j being conserved. If we evaluate the time derivative of our angle variable using canonical equations of motion, we get that the time derivative is a constant, which means the angle is given by this nu t plus beta. Doesn't this seem familiar? This must ring a bell. This looks suspiciously like uniform circular motion. And it turns out that this is in fact the case. We can actually prove this by analyzing the change in an angle variable after one complete cycle of q. And when we simplify this expression, we get that this nu, which is the time derivative of our angle variable, is just 1 by the time period of motion. Now, here's the interesting thing. We never actually solved the motion explicitly, and still we have gotten the time period of the motion. In most cases, the time period of periodic motion is what we are concerned with anyways, and hence this provides a powerful method of solving for frequencies of periodic motion without solving the motion explicitly. It basically reduces our computations. If we want, though, we can invert these relations and find q and p again, but it's not required. Let's use this to solve SHM. Now, this is the actual power of this relation. If we look at these equations over here, within 2 lines, we are able to find that the angular velocity of the system is equal to omega of the SHM itself. Note here that omega is just k by m, root k by m, if you are considering a spring. Now, we don't have a solution for the motion. We never solved Newton's laws or Lagrangian or anything like that, but we simply got the angular velocity of the system for free. If we want, we can solve it, and if we do solve it, we get these equations, which are mentioned below. Now let's try to extend this to higher dimensional systems. Now, 2 things. Firstly, in this equation, the q cannot be cyclic because it's 1D motion. The Hamiltonian must depend on something, and q cannot be cyclic. For higher dimensional motion, on the other hand, we can have some coordinates to be cyclic, in which case we simply define the action variable as ji equal to 2 pi pi if qi is the cyclic coordinate. Otherwise, we fix everything else and allow us to only vary qi and evaluate this integral pi dqi over a complete cycle of qi to find ji. And as before, we can find all of the relations between these quantities, except they are now in more dimensions and there are more quantities present. We can also show that the change in wi represents the number of cycles in qi, And in the limit as time goes to infinity, the ratio between the number of cycles of Qi and the time of analysis is indeed our frequency, which is the time derivative of Wi. This allows us to solve for periodic systems in higher dimensions as well. Now let's continue and look at some other applications of the Hamilton-Jacobi principle. The first application is in geometrical optics. Now I'll not go through the complete derivation. It is pretty unintuitive, but at the end, what we get is that there is basically this equation called the Eikenel equation of geometrical optics, which is a partial differential equation which determines light's path in a medium. And we can see that this corresponds or is similar to the Hamilton-Jacobi equation. This is why we are able to explain both wave optics and ray optics, basically because they are identical formally to classical mechanics. And this is why the principle of least action, when expressed in what is called the Jacobi form, results in Fermat's principle of least time, which we discussed at the beginning. Light takes the quickest path between 2 points. The reason is because, formally speaking, classical mechanics and geometrical optics are the same. There is literally no difference between them, except that there is a constant of proportionality added to the terms which are related to each other. Let us evaluate these constants of proportionality, and using some concepts of wave mechanics, let us see what happens. And if you see this result, it turns out that this result is the time-dependent Schrodinger equation, which we have shown to be equivalent to the Hamilton-Jacobi equation in the limit that h bar tending to 0. So in the limit h bar tending to 0, quantum mechanics becomes classical mechanics. We also get the de Broglie wavelength, which is h by p, for free. Thus, we can formally prove concepts in quantum mechanics using just classical mechanics. This showcases the power of the Hamiltonian formulation in its ability to be extended beyond the field for which it is originally intended. We can also use some higher results in classical mechanics from the Hamiltonian formulation into stuff like electromagnetism as well. Specifically, if we define the stress energy tensor, an important concept in electromagnetism, there is a classical counterpart to that. So I hope you guys took away something interesting or useful from this session. Thank you for attending this meet. We will now open ourselves to questions. If you guys have any questions, please just type them in the chat and send it. We will answer it for you. Thank you, Aryan, for the positive words of encouragement. Yes, the references which are required to solve the assignment and the assignment itself, along with this PPT and a condensed form of notes that we have created, will be sent later in the group. So stay tuned for that.